Welcome back to Physics 30. So we're going to continue on with our lesson here. So I gave you guys a little bit of a homework, I guess, to do. Here's a couple of bell work questions. If you haven't done them already, pause the video and try both of these bell work questions using the two-hand rules from last lesson, I should say. Okay. So we're going to draw out the magnetic field on both of these here. So remember, our magnetic field is denoted by the capital letter B. We haven't talked about the units yet for that. The magnetic field units is called a Tesla. We'll get into more what are the units in terms of newtons and coulombs and meters and seconds and stuff later on. But the main unit variable is called a capital B with a little vector arrow on the top because it does have direction. It's a weird direction because it's going circular. It's going in loops. So we're going to determine the magnetic field in this wire here. Let's imagine this is a wire with the electrons going into the page. So remember that's what that stands for, into the page. All right. So to determine the electron flow in both of these, actually, you can see the electron flow here going down through this blue wire here. We're just going to use our left hand because that's what the left hand is. It's for the negative charge. Our right hand is for the positive charge. So I'm going to use my left hand, right? And then I'm going to put my thumb in the direction. This is the first hand rule. In the direction of the charge. So that's going into the page. So actually it's going to go this way, into the page. So towards my face, I guess. And then my fingers are going to curl around. And that's going to be the direction of the magnetic field in this situation. So it's going to go around in a counterclockwise motion. Right? So you put your thumb in the direction, so your thumb is going to go into the page here, and it's going to go around in that counterclockwise motion. So that's what this magnetic field is going to look like. All right? And we're going to have concentric circles going around in that direction there. Okay. So you're going to follow the same rule for the next one there. So you can see my electrons are flowing down. So again, I'm going to use my left hand. I'm going to point down, and then they're going to wrap around in this direction here. Right? So they're going to go out of the page on the left side, around the front, and then into the page on the right side, and then around the back. So to note that, we're going to say it's going to come out of the page on this side. So that's where my fingers are coming out there. I'm going to wrap around and then go into the page on the other side. So I'm going to put a bunch of X's on that side to denote that they're going into the page. So they're going over the top this direction. Okay. So that's my magnetic field for that one. Okay. So the next one here, we're going to use our second hand rule to do this one. So you have to look very carefully at the picture here, trying to figure out, okay, what is the orientation or the way the wire is curling here? It's very important to know which way the wire is curling. I'm not too concerned at this point. Well, actually, I'm pretty concerned about which way the electrons are going, because that's in the second hand rule, that's the direction your fingers are going to curl, right? So let's look at what's happening to electrons here. The electrons are going up the wire. They're going up the back side and then down the front side. So they're going up the back side, over the top, down the front, and then up the back side again. They're going to continue this kind of pattern. So they're always going down the front. So they're going down the front, up the back side there. So going down the front, up the back side. So you notice that when I do that, so down the front, up the back side, you notice which way my thumb is pointed. My thumb is pointed towards the left here. So that means that my left side on this one is the north. So that my thumb, in that rule, my thumb points towards the north side, and then over here, by process of elimination, if this is the north, that's my south. Now, if I'm going to draw the magnetic field, it says determine the direction of the magnetic field generated in this question. So I determine which one's my north and which is my south. That doesn't actually mean I've drawn the field so far. So I'm going to redraw this now. I'm going to pick a different color here. I'm not going to redraw it. I'm just going to draw the field now. So the field comes, remember the rule, comes out of the north Maybe I should make that a little bit nicer. And it comes out of the north into the south. Out of the north into the south. Out of the north into the south. And then you can create these little loops on the side here. That's probably going to happen as well. Now, they don't stop at the south, right? They don't terminate there. These ones don't terminate. They'll continue the loop through the magnet or electromagnet and then finish off the loop. So these electric field lines or magnetic field lines are going to do this. And they're going to complete their loop. And you can see that the inside of the magnet, this electromagnet here, the concentration of the magnetic field lines are really, really concentrated. So that's where the magnetic field is going to be the strongest. And you can see out on the outside up here, in this area up here, that they're really spread out. And because they're spread out, magnetic field lines are going to, or magnetic field strength is going to be weaker there. So the strongest part of an electromagnet is within the magnet itself, or really close to these poles, because that's where the concentration of the field lines are the most. Okay. So what we're going to do now is we're going to talk about not just a wire moving, just the magnetic field caused by a wire or caused by a curl of a bunch of wires. We're going to just talk about maybe the interaction between a wire and another magnetic field. How do they interact? And what we know is that, or moving charge within a magnetic field. What we know is that if we have two fields, we have a force. That's what happens when we have electric fields. That's what happens when we have gravitational fields. That's what happens when we have magnetic fields as well. Okay, so we're going to talk about the moving charges in these magnetic fields. Now, what Oersted said, remember what Oersted said about moving charges? I can go back to a previous slide, one of the first and second slides of this. Is that a moving charge produces a magnetic field. Now, if I put a magnetic field inside another magnetic field, so here I'm talking about a moving charge and a magnetic field. If I put two fields together, it creates a force. So let's look at a moving charge in a magnetic field. So here's a simple picture that we have here. Now, you can see that there's these kind of weird imaginary magnets right here. So I'm just going to highlight one of those. There's this weird imaginary magnet right here, and there's a weird imaginary magnet here. Now, remember in the solenoids, if I just want to go back here, there is no physical magnet here. The north is only defined by which way the lines are coming out of this section over here. So this is my section of lines that I have here. I have a bunch of lines coming down the middle here. And because they're coming out this side, we call that the north. Because they're going in this side, we call that the south. I could have put that section of lines anywhere. I could have said, okay, what if this is the section here? If that's the section here, because the lines are coming out the right side, that's my north. Because they're coming into this side, that's my south. So there's a magnet. There's a magnet there as well, where there's a north on one side and there's a south on the other side. Okay? So we could do that with any field line. So if I draw a little field line here, you can see that I have some field lines from the north going to the south. So I have these two magnets. I've got a magnet here, I've got a magnet over here. Now these magnets could be attached like a kind of in a horseshoe shape. They could be two separate magnets, it doesn't really matter. But the lines are going to come out of the north and into the south. Okay? So they have a line drawn here on the top that represent that. So there'll be a line coming out of the north into the south. So there's a line right here. Now, if I were to draw a magnet, so just a kind of a section here, I would look at that and say, oh, there's a line coming out this side, so that must be the north side. There's a line coming in this side, it must be a south here. And I could draw any little magnet if I want to. So here I could say there's a north and there's a south here. So there's a kind of a invisible magnet here. I could do it on the bottom as well. All right, so the same orientation. So it's coming out this side, so that's why this is the north. And then it's going in this side, so that's why it's called the south. Okay. Now, when we draw these lines here, so this little circular one, remember that's our hand rule, so that would be a thumb going into the page. All right, we're going to use our left hand again. So a thumb into the page is going to wrap around in that counterclockwise motion, sorry. And you can see it's already drawn there. So we've got these lines going around in the counterclockwise direction. And you can see if I drew this magnet here, there's a line going into this side, so that's the south. And then there's a line coming out of this side, so that's the north. And you can draw one on the bottom, like they did here already, right? And there's a line coming out this side, so that's the north. There's a line going into this side, so that's the south. So to figure out what's happening here, in terms of forces, because now I have a magnetic field inside here caused by this moving charge. So this charge will assume that because of the way the orientation of this electron moving into the page. So that's why we're using the left hand there. So it's producing this magnetic field. It's inside this external magnetic field produced by these two other magnets here. Now, if I have two fields, like I said, there's a force. So let's look at these magnets here. So we have a magnet on the top here, where I have a north and a south here. There's a north and a south beside each other. And what I know from one of our rules is that unlike poles, a north and a south attract each other. So this magnet, this invisible magnet here, is going to get pulled upwards. But that magnetic field is produced by this charge. So this charge gets pulled upwards. Okay? This magnet on the top gets pulled downwards. But it's an imaginary magnet, it doesn't really exist, but it's produced by these two magnets on the outside. So these two magnets on the outside are going to get pulled downwards. Now, usually these two magnets are kind of clamped in there. They're stationary. They're not going to move. So they're not going to move. But this one here, because he's not stationary, because he's not clamped in there, he's moving through space. Because he's moving through space there, or going this way, I guess. He's free to move up and down. So he's going to get forced up because of this interaction on the top here. Now let's look at the bottom. Here I have a north and a north, right? And a south beside each other. So when I have a south and a south, or a north and a north, like poles, just like charges, are going to repel. So these two are going to force each other away from each other. So this is going to get forced up. Well, because that's part of this magnetic field caused by him, he's going to have a force going upwards as well. Okay, so there's two forces upwards on this one. And then because that got forced up, this is also going to get forced down. So that means that these two magnets are going to get forced down as well. Okay. So I'm not too concerned about these ones over here. They're stationary, nothing's going to happen with them. But this is what I'm worried about here. These two forces are going upwards. So vector addition, just add them up. So my overall net force is going to be upwards in that case. Now there's other forces there, but they're all going to kind of cancel each other out. There's forces left, there's forces right, they just cancel out. Kind of up at angles and downwards at angles. But these are the two forces that don't cancel out in this case. These two forces pushing up, one pulling up and one pushing up. But they add together as one overall force, and that's our magnetic force that I'm worried about. These two things are magnetic forces. Okay. Now, that's good. So I could do this. I could draw out using my hand rules, going from the left to right, drawing my magnetic fields, drawing my circular magnetic field caused by that moving charge. I can draw these invisible magnets. I can then look at how they interact with each other. That's fantastic. You can do that. But there's a shortcut. It's called the third hand rule. So the third hand rule allows this third hand left rule or right hand rule, depending on which kind of charge, but we're going to use the left hand because it's negative, specifies how we can determine the direction. Not how big the force is, but the direction of the force. So what we're going to do with the third hand rule is you're going to have a palm, or you could do kind of like this kind of trigger one here, like where these fingers are kind of pointing down. Now, the important part about this interaction is everything is at 90 degrees to each other. So these two are at 90 degrees to each other. These two are at 90 degrees to each other. And if I were to draw it this way, these two here are at 90 degrees to each other. Right? Everything's at 90 degrees. If you remember the video that you watched yesterday or the previous lesson, she talked about that as the angle changes, the forces change, but the maximum force is always at 90 degrees. And that's always going to be the direction of the force too. It's always be perpendicular to the fields and a bunch of other things too. So I like the palm way. You just have to kind of imagine that there's something coming out of the palm, right, at 90 degrees. Now it's nice that the palm way, because what's going to happen is the palm is the force. So what's coming out of your palm, or this pinky ring finger combo here, that's going to be the force that we're trying to find the direction of, right? Now, it's very important that you use the left hand for negative charges and the right hand for positive charges, Otherwise, you get the direction wrong, right? So imagine that we have this arrow, this force vector coming out of my palm, okay? Now the other two parts of this, my thumb and my fingers. Now what you do with your thumb is you put it in the direction of the particle, okay? So that's going into the page, so I'm gonna put that towards me. Okay, so my thumb's towards my face right now. The fingers are in the direction of the external magnetic field, right? So that's what it's gonna look like now. So my fingers point in the direction, so my fingers are the little arrows. You can see on this picture, they're going this direction. So let me just highlight that. So my field is going this way, the external field. I'm not worried about the field caused by the moving charge. That's going that counterclockwise motion, but this external field. So that's the direction my fingers point. So my fingers point in that direction. It's kind of hard. The orientation of the camera. Okay, there we go. So it's going to go that direction. The thumb is going into the page, right? Then my palm, you know, is that, imagine that arrow pointing upwards here is going up. So this palm is forcing upwards. And you notice that those two arrows are pointing upwards as well. So this here are going upwards. So draw that again. So my thumb into the page, or into the page, into my face here. Fingers in the direction of the magnetic field. So I'm going that direction. My force is upwards here. Okay. All right, so that rule is explained a couple times down here. So here's my third hand rule. It just talks about, this is just the words of what was said. So using my left hand for negatively charged particles. So let's make sure this is a negatively charged particles. I can use my right hand for positively charged particles, but this is for negatively charged particles. Oh, I'm hitting the wrong button on my thing here. Okay. Negatively charged particles. I would use the right hand for positively charged particles. So I can use my right hand for positive particles, right? The rule still applies. So everything down below just talks about, instead of electron flow, it maybe be proton flow or positive ions, such as an alpha particle. Something that's positive, I'd use my right hand instead. I'd use my left hand for negatively charged particles. Okay, so you place your fingers in the direction of the magnetic field. This is the external magnetic field, not the direction of the circular magnetic field caused by the moving charge, but the external ones. The external ones are usually just straight lines. So you just put your fingers in that direction. Then you put your thumb in the direction of the electron flow. Now this also works in wires, and you're going to see that later on, to determine the direction a wire is forced. And we're gonna do a lab on this. It's kind of a virtual lab where I actually hook up the experiment. I'll take a video of it. We record data as we go, and then you do the analysis part to determine maybe the magnetic field strength of the two magnets within my little device that we created. You'll see later on when we talk about the lab. Okay. And then the palm, my palm is the force acting on the wire or the charge, depending on what we're talking about. Like it could be a free moving charge or charge moving through a wire. They both do the exact same thing because a charge moving through wires is just electrons and moving in a direction. So you still use the hand rule to determine the field around the wire or the field around the charge. So exactly the same. And then you put that all in one orientation like the previous question, and the palm just tells us which way it's going. So imagine that charge is going up, the field is going to the right in this picture, and then my palm is going into, or out of the page in that case. It's going out of the page. Okay. So here's the little picture of what it looks like. Right? So my force is my palm. The fingers are pointed in the direction of the external magnetic field. So my external magnetic field comes from the north, out of the north, into the south, out of the north, into the south. So that's my magnetic field, right? There's going to be other fields going like this way, back towards the negative, and there's going to be other fields coming this way from the other positive on the other side of that magnet. I'm just worried about the field here. Generally, pretty much in a straight line. We're using the left hand here, so you can see this picture of a left hand. It's moved. This charged particle is moving this direction, so that's the direction of my thumb. And then my force is, in this three-dimensional picture, is kind of going downwards into the page a little bit. They tried to make this as three-dimensional as possible. So you can kind of think this is a three-dimensional arrow pointing down like that. Nice little three-dimensional arrow. Okay, kind of like that. A little program that they have online. There's a program through National Mag Lab, and National Mag Lab has this thing called the Magnet Academy. You can search that on Google Classroom. You can go down to the link on the bottom of that PowerPoint there. Type it in. There's lots of good interactive tutorials here. A lot of things that are beyond the course, but they're very interesting, like Barlow's wheel we don't talk about. How do we use this kind of magnetic induction that's caused by moving particles, moving charges, to determine the speed of a bullet? How does a Daniell cell work? There's a few things that we're going to pop up here later on, like how does a DC motor work? What is a galvanometer? Some of these things we might look at through the course. I might load these up. We already looked at this magnetic domain one, these magnetic wires. So we looked at a few of these already. They're very interesting. The one app which I wanted to use out of this one has a glitch in it. It's called cathode ray tube. The glitch about this is that as soon as you start moving the magnet polarity flip, and it gives you the illusion that something else is not supposed to be happening. It's going the wrong direction. But here I just took a snippet of what it is. Here's a little snippet of this Mag Lab, and just look. Let's just try to predict what should happen. I do have another more plain-looking applet loaded up here through the Physics Avery. It's a very similar kind of little cathode ray tube. And so what is a cathode ray tube? So let's go back to my picture here. So a cathode ray tube has a cathode on one side, an anode on the other side. If you remember from chemistry, the cathode is where the electrons are going to. They want to go to the cathode. That's the definition of a cathode. So electrons are traveling to this cathode. They're going to get bunched up here on this little plate here, and they're going to shoot off here. So a bunch of electrons are now shooting off towards this kind of little plate here. But in the plate, there's a little slit here. And then a beam of electrons is going to travel through this kind of fluorescent tube here, just like how a fluorescent tube works in classrooms. Not these ones because they're now all LED, but old ones. The electrons would hit certain particles in here and fluoresce them. They would cause them to be excited. It would glow, and you would see the beam. Now, we have the electrons traveling through here. So that's going to be your thumb in the thumb hand rule, my left hand. So my thumb's going to go in that direction there. I want to know if I were to move this magnet downwards, which way would these electrons be deflected? So let's imagine we look at these here. It's going from north to south. So that's going to be my magnetic field. So if I were to kind of visualize that, my thumb is going over to the right there. My magnetic field is going from north to left. You could see here, my palm is pointing down. So I would make the assumption that here, my palm would face down, so this beam would get deflected downwards because of the force. So it would kind of push down. Now, if I try to run this lab, this little thing here, you can see that it starts off north-south here. It's going to flip. Yeah, okay, it's going to flip by accident. I just want to see if I had a bigger one of these, but it's north-south. You can see that it flips from south-north here. It does bend downwards, but there was a glitch here that these switched on the image by accident. But the prediction says it does go downwards, so it does go downwards. Just don't look at the north and south anymore. We could see it through here as well. So this is a cathode ray, very similar. We got all these electrons being shot off on this side over here, being focused down by these little beams. It's actually being accelerated here. This is a cathode ray tube that J.J. Thomson used to discover the electron. But we just know that the cathode ray tube at this point is an electron. Back then, when they were experimenting with this, they have no idea. They just knew that they were negatively charged particles, and J.J. Thomson went along and discovered that, yeah, it's just a beam of electrons. That's what this is. So these electrons travel through here. Not too worried about the positive plates. I can turn on the positive plates here and I can deflect them up. So I can say, okay, let's give a voltage here. So these negatively charged particles are attracted towards the top plate. They don't quite hit the plate. They go over here and hit this little screen over here. All right, so let's just turn off the voltage so it goes straight through. I want to turn on the magnetic field. All right, so you can see as I turn on the magnetic field here, let me just scroll down a bit. I can turn up the magnetic field. Okay, so as I turn up the magnetic field, the beam gets deflected. So let's use our hand rule and try to figure out why that's the case. Right? So let's use my hand rule. So this is going to be kind of weird. Okay, so your fingers, so the little X's here, the little X's here are the magnetic field. You can see as I turn them off, the X's disappear. I turn them on, the X's turn back on. So my magnetic field right now is going into the base. So that's towards my face here. So I'm going to put my fingers towards my face. My thumb is going towards the right side there. It's going this, oops, sorry, it's going that direction there. All right? And then you look at where my palm is. My palm is facing downwards here. So it's getting deflected down. So there's a force deflecting this downwards. Okay. Now, we're going to talk more about this, but it's not a projectile motion. We'll talk about what kind of motion that is in the later date here. So both those demonstrations worked out for us. They both show that a moving charge within a magnetic field is going to get forced in a certain direction based on my left hand rule. All right? So let's think about this and see if we can figure this one out. So what I want you to do is pause this video. But before you pause this video, let's just think about this. We have an electron that's moving into a screen. So we have an electron right here. It is moving into the screen. I want to figure out what direction is this electron going to be deflected. It's going to be deflected up, down, left, right, out of the page, or into the page. So I want you to try that out. So I want you to pause this video,